Yeah, they are called curved mirrors, otherwise also referred to as spherical. I'll use this simple illustration and then we shall proceed. They are called spherical mirrors because they come from a sphere. From your mathematics, you may be aware that a sphere has a center, and the distance from the center of the sphere to the circumference is the radius. Now, if the sphere is shaded outside, all over outside, then this sphere, if cut into 1/2, will give us a mirror that we are going today to see or to remind ourselves as that mirror that we shall refer to as a concave mirror. With a center, which we shall label as C, and of course, the distance from the center to the circumference, we shall later on define it as radius of curvature. If a sphere is shaded inside or silvered inside, and again cut into 2/2 by dissecting, the center of that sphere will still be C, and this sphere, if we took off 1/2, the left side half, and it is silvered inside, with that line running from the center, this is still going to be looked at as our radius of curvature. What I want students to note is that most of the definitions here that we shall see will actually be hinged on the sphere, because we are saying curved mirrors, as you notice, they are curved. The concave mirror and this mirror is now going to be called the convex mirror. We shall later discover that half the distance of R for either type will generate us another point, another important point that we shall call the principal focus, and we shall later see that that distance will be denoted by a small letter f, and we shall call it focal length. Our dear students there, now I can pose a question that can get us started. Once you have seen these different diagrams, and you probably know where we generate what we used to call a concave mirror. It is called concave because it curves outwards. It is called convex because it curves inwards. It is called concave because it is silvered outwards. It is called convex because it is silvered in. It is called concave, as we shall see, because its focal point or principal focus is real, and it is called convex because its focal point is virtual. It is called concave because it has ability to form both real, virtual, magnified, inverted images. It is called convex because if you are comparing, it can only form virtual images. There are very many other differences. I want us to capture these differences as we get started. But I want to emphasize that there are two types of mirrors. There are two types of mirrors. There are two types of mirrors, and any student following this lesson, irrespective of their level by now, they know the two types of mirrors. There are two types of mirrors, and if we are asked to name them, we can say we have the convex, the concave, and the convex mirror. Concave mirror will also be looked at as diverging mirror, as converging. And then we have the convex. convex mirror can also be looked at as a diverging mirror. And we have seen that these two mirrors can be illustrated. And if I may start with the concave, as I've already emphasized, we are saying that it is illustrated by this kind of shape and is silvered out. And therefore, if this is the center, then this distance is the radius of curvature. And the concave mirror will affect light. How does it affect incident light? The light rays that are incident will always be refracted to pass through a point that we shall call the focal point. They will always be refracted to pass through a point that we shall call the focal point. And for the convex mirror, comparatively, we can say that a ray incident on the convex mirror the center of curvature is here, and an incident ray will be reflected to appear to pass through the point that we shall call, again, the focal point. Now, this focal point is real, whereas this focal point here is virtual. Again, one important fact we need to add is that students, while drawing these diagrams, are encouraged to use a ruler. I am using a free hand, but I want to encourage students to always ensure that they use a ruler. This is what would happen if we have more than one incident ray. If we have more than one incident ray, and I'm using a mirror of this type, you would obtain a diagram that should be able to look like this. That is for the convex mirror. For the concave mirror, I can fix this here as well. That for multiple incident rays, one would expect that these rays are refracted to pass through a common point that we are calling the principal focus. One would expect this to happen. Now we want to look at a question from these diagrams. If they asked us to distinguish between concave and convex mirrors, if we are asked to distinguish between concave and convex mirrors, what is expected of us? I have already mentioned the various differences between these two types of mirrors. We simply want to affirm these differences. One, we could say that for concave mirrors, one, they are silvered outwards. In other words, the silvered surface is out. These ones are silvered inside. The silvered surface is inside the mirror. Two, these ones, the concave mirrors, as you notice here, they converge light. They converge light to one point, and of course this is the principal focus. These ones diverge light from one point to an observer that is somewhere here. They see this light ray as if it is coming from there. Three, for concave mirrors, as we shall shortly see, they can form. They form real, inverted, magnified, images. For the convex mirrors, they strictly form. We can also add virtual. These ones, they form only virtual images. They form only virtual images. And last but not least, they have different uses, as we shall see. That because these can form magnified images, they may therefore be used, among others, in car headlamps. These ones form only virtual images. We shall notice that because they form virtual and upright images, they are preferred for use as driving mirrors in automobiles. And when they talk about driving mirrors, students normally confuse that with side mirrors. They should specifically mention that they are used as driving mirrors, not just in side mirrors, but they are used as driving mirrors. I will allow the students that are interested in capturing this 2 minutes to capture this information, but I want to emphasize that this information cuts across all levels. A student in senior 2 in a school where they have already covered this would confidently follow what we have so far discussed fluently and actually understand everything that we are talking about. As we proceed, I want us to quickly look at the different terms used here. But before I look at the different terms, I want to remind students that the following mirror illustrations in terms of diagrammatical representation are acceptable. The following are acceptable. For a concave mirror, I'll use cases, we are allowed as candidates to draw the mirror like this, assuming this is our principal axis, and we have maybe the points as I've so far indicated. We are allowed to represent our mirror like this if it is concave and still put our points, or we can use, last but not least, we can use this, a small cross-section at the pole, as long as we indicate the type of mirror. Of course, the shape of the mirror shows this is for concave, and I would say the above applies to all types. In other words, if it was convex, I'm saying we can also do this and present our points. We can also do this and present our mirror over there with our C and our F, and we can also do this and present our mirror over there. To the students that may be left-handed, of course, you can change the direction of the mirror. You can change the direction, what would be the reflection of what I've drawn. But any of these three options are acceptable when it comes to drawings of mirrors. Any of these. You can choose to draw a full mirror. You can choose to draw a small cross-section at the tip. And that means that this line, any ray that hits this line will actually, I have already illustrated with this one. I don't need to repeat that. With this one, this is what would happen. That a ray incident on this line would be assumed to have hit the mirror. And the ray incident here hitting the mirror would be assumed to be reflected through there. Similarly here, a ray incident would be reflected away to appear to pass through the focal point. And the same thing here. A ray incident here would be reflected to appear to be coming from the focal point. And the same thing applies here. That a ray simply incident up to this line would be reflected off to appear to be coming from that point. That is the reasoning, the simple reasoning that candidates should know. You can only use one that is more comfortable for you, but either of the three different representations either can be picked by a candidate, and they will not be penalized as long as they indicate the type of mirror in question. I want us to talk about the terms used. On average, if a question is to be asked to define the terms, they will give you two terms. There are a number of terms, and we can begin with a pole. The pole can be defined as the center of the reflecting surface. This is the center of the reflecting surface of the mirror. A student can alternatively define the pole as a point where the principal axis meets the mirror. It can also be defined as the point where the principal axis meets the mirror. I don't usually like giving students alternative definitions because they may attempt to learn both of them and end up not getting any. So I want to encourage my colleagues and the learners out there that sometimes we tend to give several interpretations of the question to enlarge the space for the candidates or the students' ability to understand, but eventually, in most cases, it may actually act negatively towards the students. Aperture can be defined as the width of the mirror, the width of the reflecting surface, the width of the reflecting surface of the mirror, but could otherwise also be defined as the distance between the extreme points of the mirror. The distance between the extreme points of the mirror. Here, if we are looking at aperture, we are actually looking at this arc. This arc, if I called it APC, that is the aperture. The other term we can look at is the center of curvature. This is the point we are referring to as C. We can say this is the center of the sphere of which the mirror forms part. It is indeed the center of the sphere, but they are saying it is the center of the sphere of which the mirror forms part. The other point we can look at here is the principal focus. This is the point we are referring to as F on our diagram. And we can say that this is the point along the principal axis. Along the principal axis, where rays originally parallel are reflected to pass or to appear to come from. Now, this particular definition for the principal axis is inclusive of the two types of mirrors. We are saying it is a point along the principal axis where rays originally parallel are reflected to pass, or where rays originally parallel appear to pass upon reflection. Now, this is very controversial here, that if they are to ask you to define principal focus and they have not specified the type of mirror, your definition should be inclusive to cover the two types. We can also look at the principal axis itself. The principal axis is ideally a line that joins the pole and the center of curvature of the mirror. line that joins the pole and the center of curvature of the mirror. We can add on the focal length. This is the distance. This is the distance between the pole and the principal focus. The distance between the pole and the principal focus. That is the focal length. Last but not least is the radius of curvature. The focal length is noted with small letter f. The radius of curvature is denoted with, of course, letter r. And we define this as the radius of the sphere, the radius of the sphere of which the mirror forms part. I have said that candidates at ordinary level, at high school, can be asked to define these terms. And usually in exam, if they are to ask you to define any terms associated with the reflection of light, they will give you 2 of these 7 terms. They will give you 2 of these 7 terms. What students should take note of, especially those that are still in ordinary level, is that these things do not change when they come to high school and they find themselves offering physics as one of their subjects. We are going to derive an expression. There is a relationship between the radius of curvature and the focal length. And I want us in the next part of our lesson to look at that relationship. Relationship between radius of curvature. I will use the symbols F and R. Relationship between F and R. And we shall base that relationship on a sketch diagram. And now that I have already equipped you with the ability to use this mirror in any format you want, we shall use that small mirror. That means that any light rays that are incident on this line are reflected, as we have seen, to pass through the focal point. So this distance will be f. This distance will be small f. And if we put a normal here, a normal is a line that ideally is expected to be making a 90 degrees angle with the mirror if the mirror is the curved one. Now, this normal would interface with the mirror at the center of curvature. And my interest here is that we are going to use angles. If I let this be the angle of incidence, I believe the students following that were in attendance from the start of this topic are aware that if this is the normal and this is the incident ray, the angle in between is the angle of incidence. But they are also aware that at this particular point, light will obey the laws of refraction, and therefore this angle is equal to I. That angle is equal to I. And from angle properties, this line is parallel to the principal focus, that's the principal axis. And therefore this angle is alternate to that angle. We shall call this point P. Maybe this is already C, this is already F. So if I call this A, I am saying angle APC is equal to angle PCF. Note that angle APC is equal to angle PCF. That is I, which is I. If we call this angle beta, and we refer to this point as N, then we are able to proceed and generate our expressions. Remember that this is now the radius. That diagram is very, very key on the derivation we are yet to make. That diagram is very key on the derivation we are yet to get out of there. Studying this diagram, I will emphasize that if I look at this mirror, I want to amplify a few diagrams from here. One is this diagram. This is a ray. If this is a ray, and we are saying it is reflected to pass through F, and we are saying this is beta, this combined is 2I. That is from this first diagram. The whole of this angle is 2I. And since these two lines are parallel to each other, we will say that since AP is parallel to line CN to CN, it implies that beta is equal to 2I. Beta is equal to 2I. And we can actually label this as number one and put a reason that they are alternate angles. Alternate angles. They are alternate angles. 2I is alternate to beta. And if we proceed and look at, can call this A, if from this diagram I picked out another diagram, I could also show. These are for purposes of emphasis. A student may not need to actually show this. I am emphasizing them so that we can actually be able to understand. If I picked the normal alone, and I pick this ray, okay, I could even pick this. It does not matter. But my interest is this angle, and now this angle, and now this angle. According to the geometry of triangles or angles, the sum of two interior angles, using sum of two interior angles, equal to an exterior angle. Someone who does not understand this could still be able to get it from our triangle PCB, if PCF. from triangle PCF, it is clear that I plus I is equal to beta, which would still affirm that our beta is 2I. That is if you do not get it right over there. Now, after understanding this, it implies that what we only need is to find beta and find I. And from this triangle, I can still say that this is our R, remember, and this is our F. So using trigonometry, and taking, for example, sine and tan, this point we called it N. We could say that this is opposite of adjacent. The tan of beta from triangle, tan of beta will be equal to opposite, which is Pn over the adjacent, which is F. But for small angles, we know that tan of beta is approximately beta, implying therefore that beta is Pn out of F. This can be equation 2. Similarly, we can look for the tan of I. The tan of I, in a similar way, tan of I would be equal to opposite using this big triangle. Opposite is still Pn over the adjacent, which is R. And for small angles, I is approximately going to be equal to Pn over R, and we can call this equation 3. So we shall substitute everything, beta and I, in equation 1. We shall substitute in equation 1 for beta and I. It is important that a student must acknowledge that for small angles, the tan of an angle is approximately equal to that angle. And therefore, we are saying that if we substitute for beta and I in equation 1, we shall obtain that Pn over F will actually be equal to 2 times Pn over R. And this implies that 1 over F will be equal to 2 over R, from where, if we made R the subject, it would give us 2F, that is 1, or we could say that F is actually a half of R. This generates a relationship that connects these two important symbols, and students should be able to define that where R is the radius of curvature and F is the focal length. And F is the focal length. This brings me to my first assignment question to those attending this lesson. This brings me to my first assignment question to those attending this lesson. I will allow you time to capture for those who are interested in capturing. And to my dear candidates, the senior 6s and the senior 4s and all the students out there, I want to encourage you not to lose hope. As the lockdown continues and as the opening of schools stays in suspense, I want to encourage you to stay focused. Stay the course, keep reading. There is nothing that starts that does not have an end. I will keep on reminding you that. So stay focused. Stay focused. Chija kugwa. Chija kugwa, as they normally say. This is a very important expression. For the ordinary level students that may be following this lesson, I want to simply remind you that for now, simply know this expression. For the A-level students, probably the S5s that may be following this lesson, you are now aware of where this expression actually comes from. Because originally, while as ordinary students, the teachers probably would not go into this detail as it would not be a requirement. My first assignment question is that you should derive this same expression, derive the relationship between F, the focal length, and R, the radius of curvature, using a convex mirror. Derive. My first assignment question here is that you derive the relationship between F and R using a point object and a convex mirror. A point object is, okay, you can use a distant object. We can consider using an object at infinity so that you don't get confused, but you can also use a point object. So let me say simply using a convex mirror. Let me not make your situation complex. Using a convex mirror. You are expected to derive that expression, to try to derive it using a convex mirror. You are aware that a convex mirror diverges light as the light moves away from. The other assignment that I will give, I will give it after some guidance. Ray diagrams. These ray diagrams are extremely important, and I would say that there are a few rules that we need to follow in order to draw them. Construction is what I'm talking about. Construction of ray diagrams. Rule number one, if I am using the concave mirror, is that rays that are parallel to the principal axis are reflected, as we have seen, to pass through the focal point. That is rule number one. Rule number two is that rays that are incident to the mirror, it is the opposite of this one. Through the focal point are reflected off parallel. Rule number three, or property number three, is that rays that are incident to the mirror through the center of curvature are reflected back along the same path. And last but not least, rule number four is that rays that are incident at the pole of the mirror are reflected off in agreement with the laws of refraction. It is only at the pole of the mirror where light rays obey, for the curved mirror, where they obey the laws of refraction. Now, to construct ray diagrams, one requires to use only two rays. two of the rays above. In order for you to construct ray diagrams, you are required to use only two of the rays above. In other words, you need a minimum of only two rays, otherwise you can use all of them, but the diagram will be crowded. I will illustrate by drawing only one, and then ask you to, and I'll give you the second assignment. For example, I will use one which is not here. For a convex mirror, I will use a convex mirror because it forms a unique image as we have seen. If this is my convex mirror, if that is my convex mirror, I have already said that a ray incident, even if I stopped it there, will be reflected off, and will appear to an observer the other side to be coming from the principal focus. Assuming that I have an object here of a known height, another ray from the tip of the object will move and will be extrapolated once again to pass through the center of curvature. This one is the first ray that I have used, and I'm also using the ray through C, which is reflected along the same path. Where the two meet, which you can all clearly see is this point, where the two meet, which you can all clearly see is this point, is where our image is formed. I'll call our image IR. And what is required is the nature of the image. How does the image appear? The nature of the image here is that the image is virtual and it is upright or erect. The image is virtual and it is upright or erect. And this brings me to a point that irrespective, I can put this as a note, that for a convex mirror, irrespective of the position of the object, we can say the image will always be virtual, erect, and formed, as you can see, between F and the pole. This, by the way, is the pole, P. And we can add that as another characteristic that is formed between F and P. Formed between F and P. This is a must, that even if you brought the object closer, the image will always be between these 2 points. It will always be virtual. It will always be upright. It will always be between those 2 points, virtual and upright. And as we move towards the end of our lesson, I definitely must use this opportunity to distinguish between the 2 types of images so far we have seen. Distinguish between virtual and real images. Virtual and real images. We can say a virtual image is the image formed by apparent intersection. Apparent comes from the word appear. Apparent intersection of light rays we can also say that it cannot be formed on the screen. It cannot be formed on the screen. If you ask to further distinguish, but a real image, on the other hand, a real image is one formed by actual. Actual is the opposite of apparent. Actual intersection of light rays. Actual intersection of light rays. My assignment right over here is that you practice on construction of ray diagrams for the concave, for image formation in concave mirror. Image formation by concave mirrors. Image formation by concave mirrors. I expect you to practice, and that means that when we meet for our next lesson, I definitely will not be able to take you through the diagrams of images formed by concave mirrors. I'll simply highlight them. I want to take this opportunity to thank you so much for attending this lesson. And as I wind up, I want to remind you that hard work breaks no bone. Hard work breaks no bone. Continue working hard and multitask yourselves. Don't only read because they say that work without play makes Jack a dull boy. I want to encourage you to continue checking and getting interested in the YouTube channel Teacher Kakuru Dennis. I want to thank the management. I want to thank the camera lady. I want to thank the producer and thank the president for continuous guidance. God bless you. Have a nice weekend.
Maryland High School.